Hello, and welcome back to another episode of our Pipeline Survey Techniques mini-series. I'm Rachel, and I'm joined again by Neil Webb.
Hi, Rachel.
Neil is an industry expert in the corrosion and cathodic protection sectors. Thanks for joining us again. Now, we've spoken at length about specialized survey techniques and recently discussed pipe potential measurement. But another important survey in the pipeline industry is a soil resistivity survey. Since a buried structure like a pipeline is in contact with the soil, it's crucial to be able to determine the corrosiveness of the soil. While I understand the concept of the corrosiveness of soil, how does this relate to the term soil resistivity?
Well, a lot of people have a big challenge in trying to get to grips with the difference between resistance as an electrical term and resistivity. So for those of you who've been exposed to our good old friend Ohm's law, resistance, voltage, and current are directly related to each other. But what about resistivity? I think the easiest way to get the concept of resistivity across is that resistivity is an electrical property of the material. So, for example, if I have a copper wire that's half a meter long, okay, and it's thin wire that is used, for example, in a piece of electronic equipment, it will have a certain electrical resistance. If, however, I take another piece of copper wire that is used for, say, electrical house wiring, same length, and I measure its resistance, it will be very different. It will be much lower, but they're both made of copper. So the resistivity is the characteristic of the copper, not of the copper wire.
Okay.
If we take that concept and bring it into soil, the resistance of the soil between 2 points in the Earth's surface is related to the geometry and the characteristic of the soil in between those 2 points. So the resistivity is the characteristic of the soil. It is its ability to conduct current. So a high resistivity soil will tend to conduct far less current than a low resistivity soil. To give you an example, wet clay is highly conductive or has very low resistivity.
Okay, so it's almost the inverse.
It's the inverse. Sandy soil has a very high resistance, very high resistivity. And the reason why that is related to corrosion is that if you think way back to our early discussions, that corrosion is an electrochemical process. It requires the passage of
an
electric current. So therefore, the ability of the soil to conduct current has a direct influence on the rate of corrosion or the corrosivity of the ground in which the pipeline is buried.
Yeah, thank you for that. Now, can you only measure soil resistivity by analyzing soil in a laboratory, or is there a way we can do it on the field?
Well, it's actually very important to measure it in the field rather than in the lab, quite
interesting.
honestly, because the pipeline is buried in the field.
True.
It's not sitting in a beaker in the laboratory. So we have techniques that allow us to actually measure the resistivity in situ. Is the term used. In other words, in place.
Yes.
And that is the important resistivity because it measures the conditions in the ground which will be dependent on the soil type and the moisture content. The moisture content, of course, is dependent on the climate. Has it rained recently or not? Are you in the wet season or the dry season? Makes a difference to the resistivity. So very, very important to measure the resistivity in the field.
Yes. Thank you. How would you go about conducting a soil resistivity in the field?
Well, the most common system that is used is known as the Wenner 4-pin electrode technique. To do this, you take 4 conductive pins, normally metal pins, steel pins, drive them into the ground at equal distances, so 3 equidistant spaces, and you only drive them a short way into the ground because if you drive them too deep, you create other characteristics. The theory is based on a point contact, but we use a fairly small probe that goes into the surface of the ground, compared to the distance over which we do the measurement, it acts as a point. So the idea behind the Wenner technique is that you take these 4 pins, you apply a known current across the outer 2 pins. That current flows through the soil from that pin to that point. If current is flowing through a conductor, it causes a volt drop.
Yes.
So you measure the voltage that is developed between the 2 inner pins.
Okay.
And the resistivity is then calculated by a formula that relates the measured resistance to the pin spacing. That then gives us the actual resistivity of the soil conditions.
Yeah. Now, placing 4 pins in the ground doesn't seem too complex. Are there any pitfalls we need to be aware of?
So yes, there are a few things that we need to be careful of. Firstly, you need to make sure that the pins are in good contact, electrical contact with the soil. And often we need to wet the pin just to get the good local content.
Yes.
You don't want to affect the overall characteristic of the soil, but you do need to make sure you've got good contact. The other thing is that you need to be careful that you don't have parallel conductors. And you say, well, what on earth are you talking about? Well, if you have a fence line at the edge of a field and you go and take a measurement parallel to the fence, then the current from your measurement is actually going to go through the fence posts.
Yes.
And give you a false reading. So fences, if you're working on a pipeline servitude where there is already a pipeline, that pipeline is going to affect the measured resistance of the soil, particularly if it is an old pipeline or a bare pipeline. Okay. And bear in mind that a lot of buried services are bare. You have bare copper wires associated with cables. You have bare galvanized copper pipes in domestic reticulation systems. You have old bitumen-coated pipes in the bigger pipeline context, and railway lines.
Of course.
If you've got a railway line running parallel to the area that you want to measure, you're going to suddenly find that you have this beautiful graph of resistivity, and then at a certain depth, in inverted commas, all of a sudden you're going to have really, really low resistance. It's not. It is the low resistance of the parallel electrical path of the railway line.
Right.
Yeah.
You indicated that the pin spacing earlier is indicative of the depth of the measurement.
Yes.
Where does the importance of depth come into play, and why is this important?
Well, pipelines are buried at some depth below the ground. And typically the pipeline will have a meter cover over the top so that it doesn't get damaged by casual excavation. In fields, agricultural lands, road crossings and things like that, it can be buried even deeper.
Right.
Now, what we're interested in is the resistivity in and around the pipe. So therefore, the pin spacing should be such that the depth to which we measure is the same as the depth of the invert of the pipeline, in other words, the bottom of the pipeline.
Yes. Yeah. Okay, perfect. Thank you. Are there any constraints to how deep you can measure and how far apart the pins can practically be?
Not really. You can put your electrodes hundreds of meters apart.
Sure.
But then you need a really big piece of equipment to generate
the current.
Yeah,
right. Yeah. Okay.
So it is limited by the capacity of the equipment that you're using. The geotechnical guys have got much bigger and more powerful equipment than the guys, the likes of us, us pipeline guys. So we use a little instrument with either a little mechanical generator or a little battery-operated generator that generates a few volts across the pins in order to drive the current. The geotech guys who are doing what they call sounding, so you may have heard of the term, they do sounding of the resistivity with depth. They have these electrodes hundreds of meters apart, and they are applying large currents to those in order to measure the characteristics of the soil to great depths.
Oh, wow.
I think the deepest that I've found that is practical with these little handheld instruments is about a pin spacing of about 9 or 10 meters.
Okay. And is that between each pin.
Each pair of pins. So you've got 4 pins, so there are 3 spaces.
Okay, and each of those
each space is the same.
Okay,
It's a characteristic of the formula, the simple formula.
Yes.
Okay, that your pin spacing is constant.
Okay.
Yeah.
All right, thanks for clarifying. Is there anything else we should be keeping in mind when measuring the resistivity of soil?
I think the most important thing, other than making sure you've got good electrical contact, is the integrity of your electrical harness, in other words, the connections that you are using. Because if you land up with a poor contact due to perhaps a cable breaking or something like that, you get an apparent high resistivity, which is actually not a high resistivity at all. It's a broken cable. And given that when you're measuring pipelines, I think the longest I've ever done in a day was something like 17 kilometers.
Sure.
In one day, taking measurements every 100 meters.
Yeah.
You're rolling these cables out and rolling them up and putting them out and rolling them up. And the connections break. And that is one of the most important things, is to ensure the integrity of your measuring equipment, and then also to note the season during which you're doing the measurements.
Yes.
We've had situations, particularly in the Eastern Cape, where the soil resistivity changes by several orders of magnitude between the dry season and the wet season. So you do a survey in the dry season, you think you've got non-corrosive ground conditions. Come the wet season, you've got a very, very different situation.
Yeah. Well, thank you, Neil. I think this has been incredibly informative. So we appreciate your time, we appreciate your expertise, and we look forward to having you back for future episodes.
Sure.
And thank you for watching. I hope that this conversation has added depth to your understanding of survey techniques. So don't forget to subscribe and turn on notifications so you never miss another episode. Thank you.